Hello, everyone. Well, I'm here to go through something that I posted a few weeks ago, um, and I thought I would tell you what it said. Its title was, I Have a Theory Too, The Challenge and Opportunity of Avocational Science. Theories of the World. Several often arrive in a single day. Sometimes they're marked urgent, sometimes they're long, sometimes they're short, sometimes they're humble, sometimes they're conspiratorial, and sometimes these days they're written, quotes, in collaboration with an AI. But there's a common theme. They're all emails that present some kind of fundamental theory invented by their authors, or perhaps their AI, about how our universe works. Well, at some level, it's encouraging to see how many people find it interesting to think about fundamental questions in science. But at some level, it's also, to me, very frustrating because all that effort being spent and so much of it so wide of the mark. I mean, most of the time it's based on, at best, high school physics, missing kind of everything that was learnt in 20th century physics. Sometimes it's easy to tell that what's being said just can't be right. Often things are too vague or tangled for one to even be able to say much at all. Well, most physicists term people who send such theories crackpots and either discard their missives or send back derisive responses. I've never felt like that was the right thing to do. Somehow I've always felt as if there has to be a way to channel that interest and effort into something that would be constructive and fulfilling for all concerned. And maybe, just maybe, I have now at least one idea in that direction. It doesn't help the situation, of course, that there are so many myths floating around about how science makes progress. Newton suddenly figured out gravity when an apple fell on his head. Einstein was a lowly clerk when he figured out relativity. When one actually studies the history of science, one finds that essentially, without exception, there's always a long and sophisticated personal backstory to advances that people make. Newton was already a top professor when the perhaps apocryphal apple fell. Einstein had got a PhD from a top university and had gone to the Silicon Valley of the time, the Swiss Patent Office. It basically never happens that there are sudden flashes of insight that come out of nowhere. And that's particularly true in fundamental physics, where a fairly tall tower of abstraction and formalism has developed, particularly over the past century or so. There's kind of everyday physics of the kind we can reason about from our everyday experience. And then there's physics of the very large and very small that's far from our everyday experience. But it's that physics that's our best probe of the fundamentals of how things work. And if you don't know it, you're at a crippling disadvantage in making foundational progress in physics. Of course, I will be the first to say that in science, conventional wisdom often leads one astray. There need to be new, fresh ideas, and often ones that challenge the foundations of things that have long been assumed. But when, as in physics, there's methodological depth to what's been figured out, that's a good place to start in making further progress. Maybe the traditional mathematical approach to quantum field theory isn't quite right, but to discard all the abstractions and generalizations that got us to quantum field theory and to return, for example, to high school physics takes us to the wrong level of thinking. Well, what's the story of my own efforts at figuring out fundamental physics? Past few years have been exciting times for me, building on basically a lifetime of science and technology to arrive, to my great surprise, at what seems to be a serious breakthrough in understanding fundamental physics and how our universe works. And while what's now our Wolfram Physics project can, at least at a superficial level, be explained fairly simply, what's underneath is quite a tower of ideas, formalism, and computational investigations. At some level, though, I'm an amateur physicist, doing science as a hobby, like the people who write to me. But under the surface, the story is rather different. Yes, for nearly 4 decades, my main day job has been CEOing a tech company. But as a mid-teenager, I started out doing physics and soon was a rather successful professional physicist. And indeed, a key motivation for my efforts in technology has always been to build tools I want for myself for doing science. So yes, over the years, I've indeed maintained what one might call a serious hobby of doing science, now, for example, with Bohm Institute. It has to be said that I'm pretty sure I wouldn't have been able to do the things I've done if I'd stayed embedded in the academic system with its increasingly strong toe the line kinds of constraints. I mean, it's been crucial that I've been in a situation where I'm free to chart my own independent intellectual path. But despite that institutional independence, I'm still routinely leveraging my rather expensive knowledge of existing physics. It's true that the new paradigm I built has led me to reject some of what has been long believed, but I've never rejected anything lightly. I always make a point of thoroughly understanding what I'm rejecting, and as part of that, it's become my practice actually to make a detailed study of its history, to see just how people originally came to believe whatever it is. So if you just catch something I say on a podcast, you might get the idea that the things I've figured out just came to me in a simple way, the simple way that I described them. But it's not like that at all. It's always a complicated process full of detailed systematic work. Central to the way I do things is the tower of technology we built over the past 4 decades. I mean, I use Wolfram language as a medium to clarify my thoughts, and I use it to make those thoughts concrete in computer experiments, which routinely produce results I absolutely do not expect. So, as much as possible, I insist on trying to understand everything from its first principles so I can be confident that I know what I'm talking about. Oh, and it also helps that I work with very talented people and have a large network that includes many of the world's leading scientists. So, yes, even if I manage to explain it simply, there's always all sorts of sophistication behind the science I do. So when I get an email that says, I just figured out physics yesterday, or there's this high school physics fact that explains the universe, it profoundly doesn't ring true. Even if someone says, an AI helped me, and there's a veneer of technical academic presentation. Well, let me talk about my 1975 experience. So in 1975, when I was 15 years old, I just started writing papers about my own physics research when I received a curious letter that's now preserved as a yellowing page in my archives. Let me show you that. There it is. So it's from a certain Alexander Gordon, M.A., Ons means honors. So it's rather British in many ways. It's written on 24th of February 1975 from Flat B, 7 Belsize Park Gardens, London, NW3. Dear Sir or Madam, I guess I was at that point somehow I'm on some form list. It starts, I am a well-preserved 62-year-old. That seemed super old to me at the time. No longer. I graduated with first-class honors in maths and physics at Edinburgh in June of 1933. So that leaves me open to patronization by the anonymous hierarchy of high-energy high priests that has proliferated since then. Of my life to date, I will say little, except that it has been wide-ranging and not too demanding in the expenditure of life's resources, so that I am I'm well set for a lengthy campaign of propaganda for my theory, which came to me some 9 years ago, after I had resat my final honors exam with a view to a research career and been turned down solely on the grounds of an inadequate performance in the quantum mechanics paper. Anyway, it goes on and with some kind of, well, I can read it some more. Every major breakthrough in science has had aspects, but high up on the list of these, if not preeminent, is the aesthetic one. Galileo, Newton, Einstein, Dirac, all must have been sustained in their efforts by the beauty and cohesiveness of the grand design. The insidious nature of the present one is such that even though all of the above pioneers were rewarded by a dazzling panorama of hitherto hidden scientific truths, there is a finality and comprehensiveness about it which tempts the hapless explainer to stammer golden things like the inarticulate shepherd who once was given a glimpse of the golden city of Samarkand. Well, anyway, it goes on. This I fear will have frequently done, as previous recipients of my half-boiled accounts will no doubt corroborate, etc., etc., etc. Anyway, it goes on and uh, talks about the what is described as the hoop hypothesis, and then presents the hypothesis was that particles like electrons and protons are in effect little loops of wire carrying electric current, and we can see the illustration, I hope. There we go, of the loops of wire carrying electric current and um, uh, being electrons and protons and things. Well, there seem to be things here that were obviously wrong to the 15-year-old me. So I decided I'd point them out. And I still have the letter that at least that I wrote. Let's see. There we go. On the 28th of April, 1975, I was at boarding school at Eton at that time, hence the my address of new buildings. The new buildings, I think, had been built in the 1840s. But so they weren't so new at the time when I was there. Eton College, Windsor Box. So, dear Mr. Gordon, and I talk about a bunch of things, but I think I was fairly polite. I'm afraid that I still remain unconvinced about your theory. There are a few points about it which I'm not really happy with. One, Dirac's theory and its results predict results which are on the whole correct. Admittedly, there is no explanation of gravity or of the existence of the strong interaction. Okay, that changed right around that time. You see, when you begin to probe small distances, the form factors should see the internal structure of the proton and electron. So far, no internal structure has been seen. There's no derivation of the E plus E minus elastic scattering form factor from unity, deviation of that from unity, at least until about 20 GeV squared. Similarly, et cetera, the meson cloud of the nucleon has been mapped quite carefully, et cetera, et cetera, et cetera. This was sort of germane to things that I was working on at the time because I was interested in whether electrons might have substructure, but his loops of wire were 1,000 times bigger than the limits that were known on the size of electrons. Anyway, I end. I hope your theorizing goes well, and I'd be interested to hear of your progress. Yours sincerely, in a rather flowery signature that has not survived the test of time for me. Well, so I was a lot younger then, and the uh, and I had a duly immature signature, and I didn't anticipate that after my first response, I'd received a deluge of letters full of elaborate handwritten calculations. I responded a couple of times, but it didn't seem to be making any headway, and so I gave up. Then I started getting letters saying, please send back my calculations. I mean, my archives still contain the envelope I prepared to do that, but I felt I should say something definitive to close things off, and I never got around to that, which I feel a little bit bad about. But looking at the letter I received half a century ago, it's striking how similar it is to so many of the emails I get today. Though today the writing is not usually so flowery and eloquent. Somehow there's an enthusiasm for solving physics using everyday thinking and everyday experience that's persisted all that time, and about which people who haven't been deeply exposed to 20th century physics developed surprisingly great conviction. What should people actually do? Let's say you're passionately interested in doing science, but you haven't had a chance to spend years learning the technical details of something like existing physics. What can you do? Maybe you have some particular idea, perhaps based on something you've heard about or read about. If the idea is an area with as much technical depth as physics, it's realistically going to be an immense challenge to develop the idea in a useful way. And most likely to really do so, you'd have to learn a whole tower of technical details, the equivalent of several years of schooling. But nowadays you might think, can't AI help? Well, If you tell your idea to a high-end LLM, it'll probably be able to produce something that looks and feels like a scientific paper. But unfortunately, with almost absolute certainty, the paper will ultimately be complete nonsense. At a sentence by sentence level, or even a paragraph by paragraph level, it may seem okay. But assuming your idea hasn't already been worked out somewhere on the internet for the AI to read, then regardless of how much reasoning the AI claims it's doing, it's almost astronomically unlikely that it'll produce anything that hangs together. But while AI on its own isn't realistically going to help, computers and computation potentially can. Because if you can get your idea beyond pure words to something more formal and precise, then it's potentially a different story. Because then you may be able to do the kind of thing I've routinely done for so long and use the power of computation to do the heavy lifting to explore your ideas. And yes, it's an ideal use case for Wolfram language, because Wolfram language not only lets you describe things to a computer, it also lets you formulate your ideas in a clear computational way. And these days, there's even a good chance you'll be able to use our AI notebook assistant to help you get started. But the thing to emphasize is that if this is going to work, you'll at some point have to actually understand with clarity the computational language code to describe your idea. It's a high bar to reach if you just start with words. But if you can reach it or get somebody to help you reach it, you'll be off and running, able to do real science, relying on a computer and Wolfram language, just like so many of the world's leading scientists do. If I'm realistic, though, only a tiny fraction of the kind of avocational science emails that I receive seem even close to being amenable to that kind of formalization. And most of the time, I just feel like they just picked the wrong battle. They're trying to solve physics and beat Einstein. But as I talked about, you have to have a lot of technical knowledge to even credibly get to the starting gate in such an effort. So is that the end of the story? Are the front lines of science just closed to anyone who isn't in the priesthood of highly trained scientists? Well, you've got to expect to do careful, systematic work. But the good news is that these days there's a certain opportunity for great foundational contributions to be made that don't depend on all the technical details of, say, existing physics. Yes, in these years, there's a way for someone without all that technical training to do foundational science that's significant and thoroughly original and potentially has all sorts of philosophical as well as scientific significance. It won't be something that kind of swoops in and solves physics, but it can be a building block that might even apply to physics and that represents a lasting intellectual contribution. As it happens, it's been my own work over the past 45 or so years that perhaps most clearly highlighted what's possible. But ultimately, what's opened up the opportunity is that great intellectual development of our time, the computational paradigm. Unaided, there will be no alternative but to toil through all those technical details to reach frontiers of science. But what we're learning is that thinking in fundamentally computational terms provides something transformative, a way to see directly deep into the foundations of science, and for those who choose to use it, a way to chart a direct path right to the frontiers. I mean, in the past, it wouldn't have been so clear. But particularly now with our physics project and everything that's followed from it, I think we can be confident that there are meaningful computational foundations to be found for theoretical science underneath, for example, fields like physics and mathematics. And it's these foundations that, with the help of computation, give us access to a new frontier of science. It's all about exploring the computational universe, the universe of computational possibilities. The computational universe is infinite, and there's a place in it for everyone, a place that's never been visited before, where there's new science to be found that, once found, will stand forever. These days, I have a name for this kind of science. I call it Ruliology, the study of systems with usually simple computational rules. In some ways, one can view Ruliology as the ultimate theoretical science, the science from which other sciences must flow. I myself have been doing Ruliology for 45 years now, and it's been at the heart of most of the discoveries I've made over all those years. But in all that I've done, I haven't even begun to scratch the surface of what's there to discover in Ruliology. Pick even perhaps the best explored part of Ruliology, the study of cellular automata. Going out into the computational universe, one can instantly find examples of all sorts of richness that one can be pretty sure nobody has ever seen before. Here's a kind of example picture of that. So each of these elaborate pictures is like a world unto itself, a system with all sorts of detailed behavior that can be studied. It needs scientific creativity to figure out what to look at, and it needs a certain clarity of thinking to keep track of what one might find. But with Wolfram language as a tool, there's no limit to the explorations one can do. Create a computational essay describing them, and you'll have made a clear contribution to science. Don't expect that the details of what you'll see will immediately relate to phenomena, say, in physics. Even if you're using hypergraphs, multi-way systems, and so on, you're inevitably operating far below what physics over the past century has explored. But the more broadly and deeply you investigate, the more you'll have a chance to find core phenomena in Ruliology that'll flow through to lots of other places, including potentially physics. By doing computer experiments, you'll develop a new kind of intuition. I don't think I've ever seen anyone who isn't at first surprised by what they see out in the computational universe. Well, but with the intuition you get from looking in the computational universe, you'll get a sense of what you might explore there. And you'll get a real kind of 21st century way to think about science. Something that in the end might lead you not only to specific scientific conclusions, but also much deeper and more general conceptual or philosophical conclusions. Everyday experience of the world gives one a certain intuition, whose implications have been well worked through over the millennia. But experience of the computational universe is something new and something from which, if one successfully internalizes it, one can derive fundamentally new insights about the way things work. So what does this mean for the stream of emails I receive? Just sometimes there's already a piece of Ruliology, where there's a clear computational phenomenon that the mail describes. And when I get such a piece of mail, I think to myself, yes, there's something that'll be a surviving contribution to science. But far too often, the thrust of the mail is instead, here's the theory I came up with by making an argument largely with words. Centuries ago, that might have been par for the course. But now nothing like that has a serious chance of reaching the frontiers of something like physics. And it could be that the only way to reach those frontiers would be to learn the whole tower of existing physics. But Ruliology provides a unique shortcut. Ruliology is a field so vast and so comparatively new that in a sense we're inevitably all at some level beginners in it. I've spent years building the tools for it that through Wolfram language are now available to everyone. So now we're all able to explore it together. When one makes a discovery in Ruliology, there's a certain abstract permanence to it. That rule you found will always do that thing. And it's something that, in a sense, helps to elevate us beyond our mere human existence. We've come upon something that's forever, that will always be that way. And it's hard not to feel a sense of awe in being able to discover a thing like that and to know that no human in history has ever seen it before. I'd like to think that this kind of thing is the essence of what people seek when they try to come up with their theories of physics. But the difference is that a solid piece of Ruliology, likely complete with striking and unexpected images, represents a real achievement in science that one can validly be proud of and that can enter the long-term canon of science. So please send Ruliology, not yet more vague theories of physics. Let's take all that energy and direct it to that foundational mission of 21st century science, the systematic exploration of the computational universe. Well, I had kind of one extra piece that I included in what I posted was a box entitled, How Do I Get Started? So the best way to start studying Ruliology is to start doing it. Check out some of the things I've written about Ruliology, and you can pull those up here. If you go to my writings, you will find there's some lots of pieces about Ruliology, different angles on Ruliology, from nested recursive functions to the Ruliology of the forgotten code 10 to questions about mathematical proofs, tiling as multi-computational phenomena, generative AI, games and puzzles, physicalization of metamathematics, all these kinds of things. But one of the things about anything I write is you can click on any of those pictures in the things that I write. And any picture, you can click on it and you get the Wolfram language code to reproduce that picture. So, start by finding a picture that looks interesting, try modifying its code, try to understand what's going on. We're planning to put in place a kind of systematic educational program for Ruliology, as well as setting up a new kind of modern venue for publishing Ruliological investigations. And we're planning to provide infrastructure to help develop a systematic worldwide Ruliological community. We're just getting started on those things. I added a link to add yourself here to learn about developments with doing Ruliology. And I'm happy to say that a lot of people have added themselves to that. And hopefully we'll have some good things to say very soon as we start to build out kind of the field of Ruliology as something that there are materials to learn about, materials to connect with other people through, and so on. So this is kind of a work in progress for us, but there's a lot you can get started with in Ruliology by, among other things, reading lots of things I've written and starting to actually run the code that shows up there. I think one of the things to say is when you start doing Ruliology, the thing it is both ennobling and humbling. Ennobling in the sense that you're doing these very foundational kinds of things that nobody has done before, and humbling in the sense that when you run computer experiments, they often don't come out the way you expect. They often, as I often say, the computational animals are always smarter than we are. You think you have understood what they're going to do, but they'll always have some bizarre kind of behavior that you never anticipated. And that's something that is both humbling and also in many ways exciting. You're really making discoveries that were not already obvious. They're things that you have to do the experiment to find out what's going on. Well, that's for once a fairly short thing that for me to go through. I guess I can have some discussion here. It's a question from Trevor. Do you ever get a submission that makes you go, wait, that's actually kind of interesting? Or is it usually just wacky stuff? Yes, it's sometimes interesting. It's much more often interesting when it's more, several different cases. One, it's basically a piece of Ruliology. Two, it's more conceptual, but the concepts are clearly enough explained that I can actually understand them. Sometimes it's that it makes historical connections of some kind and kind of knits together things that have been sort of disparate threads and provides some way to understand perhaps something I've done, say, oh, it's related to something this philosopher, scientist, whatever, had done in the past, and really can tightly make that connection. Making that connection loosely is not very useful. It kind of is like, go read the 10,000 pages this philosopher wrote, and maybe you'll find something that's relevant to what you've done. That's not terribly helpful. But it's like, here's a quote which you can understand, and this is how this relates. That's a lot more helpful. I would say that if I look at my mailbox, there's sort of clusters of things that come in. There are a remarkable number of theories of physics at the rate of, I don't know, for some reason they've even increased in the last few weeks. It's like several a day. And those are mostly when they're just pure theory of physics without some kind of Ruliology or sort of core connection to things. They're usually really quite wacky. When they're more conceptual, it's more interesting. These days, one of the frustrating things is that they're often dressed up to look like academic papers, and they have all kinds of formulas and wording and so on Of course, the word delve is always a giveaway that it was an LLM that wrote it. And also somehow the formatting has started to be a giveaway. It used to be the case that when things were nicely formatted with tech and other sort of academic, publishing machinery, that was kind of a sign that this was something that people had sort of worked in a more sophisticated way on. But now this sort of almost the exact opposite is true. If it's sort of a perfect, well turned out thing that uh, has sort of, beautifully done section headings and bullet points and so on, that's probably was too much work for a human. That was probably done by an LLM. I got something just recently. Somebody wrote for me, not an unsolicited thing, something that I'd asked for. That well, partly at least, that was this whole elaborate mathematical thing which I'm like, this is LLMery. And then there were some pieces that had spelling mistakes and bad grammar and so on. It's like, okay, the person actually wrote those things themselves. Um, and it was kind of we've kind of inverted the situation there. But unfortunately, with LLM stuff, people say, look, my LLM did something interesting. That is hopeless because the LLM has made it so that it has the veneer of kind of academic appropriateness and so on. And it just takes more effort to drill through it and say, wait a minute, I have to think about every piece of this. And, when you put all those pieces together, no, this makes absolutely no sense at all. But that's a lot of work. One isn't going to do that. I think the thing that also helps a lot is, we always say to people, tell us how this relates to what we've done. And when that's precisely laid out, that again helps very much. I mean, when people say on page 742 of a new kind of science, you say this specific thing, and here's another thing to say related to that. That's a kind of a, yep, that's interesting. That's a, that for me has some kind of context, some cognitive hook. If it's just like, oh, there's this general thing and it comes out of common sense and so on, that's much less promising. When there's actual Wolfram language code, among other things, you can look at the code, you can see what was going on, and you can see, is this a thing that has an interesting structure? Is this a thing that was written by an LLM? Is this a thing that's really very trivial? What is this thing? It provides this kind of formal, precise representation of what's happening. Let's see. Haley asked, what made you decide to write about avocational science right now? Was there a particular experience or submission that prompted this? Actually, it was we have sort of things we send back to folks who send these kinds of things in, and we were about to redo those uh, those kind of templates for letters that we send back, and somebody, a writer, works with me, with a company, had taken a crack at writing these, and I'm like, this is great marketing writing. This is not going to cut it as a template response to people who write to me. And so I'm like, I guess I better write this myself, as I had written the previous one. Um, and so that led me to like, well, what do I really want to say? And then I thought, well, I should just write out what I really want to say. And that's what led to writing this piece. Uh, Hyvie asks, given how overloaded the scientific community already is, wouldn't encouraging amateurs just make the noise problem worse? Well, it depends what they do. If they work in areas that the scientific community is not all over, so to speak, then they can make progress in places the scientific community is off doing its very institutionalized things in these very specific areas that have developed for a long time. But there's these great new opportunities where there isn't a large sort of academic kind of concentration at this time. I mean, in the past, there have been many fields that have developed through largely through avocational amateur science. For example, natural history in the 1700s, 1800s. That was really a story of people going out and collecting all those butterflies and so on and so on and so on. Still happens today, but there's a lot more, the whatever 10 million species or so on of the Earth are much better known at this point. In those days, people were routinely discovering wild species that had not been known before. And that was really a sort of everybody gets to do it. It wasn't so much the professional naturalists. There were other few of those. Uh, and what happened is the result of all of that collection of all of that information turned into things that people like Darwin and Wallace and so on could go and systematize and make actually two versions of Darwin, Erasmus and Charles, could make kind of make more general kind of statements from. I think the same was true in, well, for example, in astronomy, particularly with things like comets and asteroids and so on. A lot of work by non-professional astronomers in that area. Lots of kinds of citizen science projects. Well, these days, things like, if you want to know the where different kinds of birds live, then the online sort of bird systems are much better than what you would get from people specifically having sort of professionally tagged birds and so on. And there have been times when mathematics also had a strong amateur component. I think that was particularly true in the late 1800s. There was a lot of kind of puzzle math that kind of really sort of seeped into kind of the discrete math that started getting developed well, and really didn't develop that strongly until the mid 20th century. But um, so there are many areas that have been really driven by kind of amateur avocational kinds of science. And I think Ruliology is one that's really ripe for that, not least because there are so many people quite educated in science who do things like software engineering. And I've seen many examples of this, of people who really have the right instincts to be good scientists. They didn't climb they didn't learn the whole tower of formal detailed physics and mathematics and so on, but they have all the right instincts to be really good scientists. And they also have the methodological knowledge of computers and so on to be able to do things with Ruliology. And that's why I think it's such a great field for kind of development along those lines. And I think that when is more developed in Ruliology, I mean, a lot of what I've done takes sort of ideas, lots of specific ideas and results from Ruliology, and eventually concludes things like the idea of the Ruliad, or the idea of our physics project, or foundations of mathematics, physicalized metamathematics, and so on. Those all came out of doing lots of Ruliology and then sort of being able to see what the big picture was and go from there. With respect to the question of was asked before about what's interesting. The permanent cautionary tale of that is Ramanujan. I think it was 1913, maybe, that Ramanujan, who was quite educated in math, but was working at that time as a clerk in the port of Madras, I think, in India, was and he got all his day job done in very short time because he was a really fast calculator. But what he did with his really fast calculating is he figured out all kinds of number theory and other kinds of mathematical ideas that he did by largely doing experimental mathematics with a computer, himself as the computer, not a computer of the kind that's made with electronics and so on, but a human computer himself doing the computations. And he had figured out a lot of interesting number theory and other kinds of things, a lot of bizarre relations between mathematical functions and so on. And he sent letters, well, he sent a couple of letters, one to a man called Neville, who didn't take it seriously, and another to a chap called G.H. Hardy in Cambridge, who looked at all these letters and said, this is just too bizarre. You couldn't even make this stuff up. And the and so then Hardy kind of took that seriously, brought Ramanujan to England. Hardy was, I think, always very confused about what Ramanujan had done, because he's like, how did you prove this result? Well, Ramanujan didn't have a proof for that result. It was a piece of experimental mathematics. And Ramanujan had a good enough intuition to know what was likely to be true. I think Ramanujan eventually, in frustration, started telling Hardy that, it comes in my dreams from some Indian goddess or something, which was, I think, just his sense of humor, so to speak, which Hardy, I don't think, had such a good sense of humor. But the uh, the thing, I mean, you can kind of tell Ramanujan's methodology because a lot he got right and some things he got wrong about, for example, the distribution of prime numbers. He thought something was true, and it is true up to some absolutely huge number. But at 10 to the 10 to the 10, something or other, it stops being true. But Ramanujan couldn't reach that by his experimental mathematics, and his intuition kind of misfired in that particular case. But in many other cases, it fired correctly. Anyway, I was writing something maybe, oh gosh, nearly a decade ago about Ramanujan, and I was writing about how the one sometimes gets it's much rarer actually that one gets maybe that's something specific to me, but I don't think so. It I think used to be the case that one got more things about mathematics than about physics. It's really gone towards physics in recent years. I mean, in the past, the physics uh, communications tended to be, I've disproved relativity. It's kind of, I've beaten Einstein, I've disproved relativity. That seems to have gone out of fashion. Then there was, actually, perhaps one of my all-time favorite pieces of mail like this is uh, the invention of a perpetual motion machine. Perpetual motion machines are a complicated story. I've spent a good chunk of time studying the second law of thermodynamics. I could talk about the extent to which perpetual motion machines aren't as impossible as you might think they are. It's really sort of a computational problem. But forget that. The particular perpetual motion machine letter that I got, these were physical letters back in those days, came complete with a perpetual motion kit that had pieces of string and paper clips and so on, which I was almost inclined to assemble. But I think among those things are mathematical kinds of letters. And we're going to prove the Riemann hypothesis, we're going to prove the Goldbach conjecture, or we're just going to state some funky mathematical result. And I remember just around the time I was writing that piece about Ramanujan, I got a postcard from India, as it happened, that had some mathematical relations on it. Now, Ramanujan, one of the things that he worked out was that I think it's e to the pi square root of 173, I think, is very close to an integer. And many people would just said, whatever, I don't know, that's just coincidence. But Ramanujan had good enough intuition to realize that wasn't a coincidence. In fact, that nearness to an integer developed into a whole theory, and in the most immediate sense, gave Ramanujan a way to compute the digits of pi better than anybody had had before, and it's the way that was used for a very long time. But anyway, this postcard that I got right around the time I was writing that piece was also a relation that was an almost integer type relation, with I think with logs and other functions in it. And it's like, is this a Ramanujan thing or is this a nothing thing? Because just to explain, one of the things people sometimes make a lot of hay out of is sort of a numerical coincidence between this and that. So in physics, there's this constant, the so-called fine structure constant that characterizes the strength of electromagnetic interactions that's almost exactly 1 over 137. And so it's like, can you derive that? One day, hopefully, we will be able to derive that. The fact that it's 1 over 137 is a detailed feature of the fact that we're looking at it at a low energy. If we looked at it at higher energies, the number will be different, et cetera, et cetera, et cetera. But be that as it may, it's sort of an observer-dependent number, but it is, for us, at least 1 over 137. And there's a question of, can you derive that? And so people will go and say, well, I've got this set of relations or that, is square roots of pi, of e, of this, of that, of the other. And you combine a bunch of these things together and you get the fine structure constant, or you get the ratio of the mass of the electron to the proton, or something like this. The problem is, as soon as you start making these complicated formulas, there's a lot of formulas out there, and every number is close to some formula. If you just type a number into Wolfram Alpha, it'll give you a bunch of approximate formulas that can be close within, let's say, 5 digits, 7 digits, whatever, of that number. So it really isn't that significant. It's something where it's sort of the numerology, the numerical coincidences are not that significant. Now, occasionally, there will be a numerical coincidence, particularly if you have a sequence of many numbers, that is significant. This sequence of numbers that shows up in one place, you go look it up and you find out that same sequence of numbers occurs in some completely other area of mathematics. And then you realize, gosh, there's an actual connection between these things. But the idea that you get to sort of write down this formula with 7 logs and 5 cosine functions or something, and you get, 18, the ratio of the proton to electron mass, 1839, whatever it is, and you get that to 5 digits, is completely unsurprising because with that number of sort of parameters in your formula, it's easy to get anything. So, but having said all of that, there's sort of Ramanujan risk. Does one get something that really is quite interesting and one just ignores it? I like to think that I have a pretty good nose for what might actually be interesting, and I certainly have at times responded to things people have sent me that sometimes seemed quite wild, but where I was pretty sure there was something interesting there, and it turned out there was. Um, and I suppose that justifies in some sense people sending this stuff to me because I have managed to actually pick out some things that are interesting, but it's unfortunately the motif of it's a theory of physics is usually doomed. Um, I would say there's another category, and maybe this is a self brought upon myself, is things that are more philosophical and relate to the nature of consciousness and things like that. I would say some of those things are probably more sensible, but it's also harder to decode them and it's harder to know really what they were saying. I mean, if somebody sends me something that describes the nature of I don't know, conscious experience about this and its relationship to this or that philosophical tradition, it's a lot of work to untangle what that is. And I also don't know what the point is. In other words, if I say, yeah, that's might be true, it's like, so what? It's, with some of these things in science or mathematics, for example, if there was a valid, proof of the Riemann conjecture, Riemann hypothesis, then that's going to build some structure that you can do other things with. So I think um, that's kind of uh, another sort of aspect of, well, what is the thing? Now, I have to say that the other type of thing one gets is actually I don't get this that much, which is sort of surprising to me, is sort of I've just invented AGI and it's this AI in my basement and it suddenly woke up and is showing, it's a human-like behavior and so on. Maybe that's because nobody did it, or it doesn't really even make sense to talk about doing it, which is what I kind of believe. Um, but for some reason, that's a less common thing. Maybe because it's actually hard and because you can actually see if it really happened, or maybe people try it and they can tell it doesn't work. Of course, I get a lot of pitches for companies and technologies, and uh, I would say that on balance, those are much the rate of sensible ones is much higher than in basic science, much higher. Some of them are um, quite wild, quite strange biomedical devices, strange kinds of ideas about uh, brain uploading or about some kind of thing about measuring this or that kind of thing. But generally, there's more meat there. There's more real stuff. Now sometimes and there'll be um, and sometimes it's hard to tell what the story is. I'll tell you one story. I actually wrote about this. I wrote a post about this a while ago. Some people were giving me this pitch for a company, and their business plan was we'll make 1 million very tiny spacecraft. We'll send them out into interstellar space using some method of pushing them with lasers or kind of using light from the sun or something like that to push them out into interstellar space. We'll let them go out, and they'll be very tiny. They'll accelerate to a decent fraction of the speed of light. They'll get to other star systems in reasonable amounts of time, and then they'll discover extraterrestrial intelligence. They'll send back the uh, the results from that extraterrestrial intelligence. They'll bring back the technology of extraterrestrial intelligence. They'll bring it to Earth, and they'll accelerate the technology on Earth by 1 million years. Okay. Now, I have to say that pitch is one of the craziest pitches I've ever heard. And it's a pitch that I think is philosophically doomed. Because what is technology? Technology is taking what's in the natural world and kind of adapting it for human purposes. And it's easy to get technology, get things out in the natural world that do all kinds of elaborate stuff. It's just hard to make the connection with human technology. And by the time you're talking about sort of discovering extraterrestrial intelligence, whatever that means, what's the difference between a true intelligence and the weather or the magnetic field of a pulsar that's doing very elaborate things? The difference is those things are not aligned with kind of human style intelligence. But there's, I think, no sense in which there's a fundamental distinction between those things in terms of sort of the abstract notion of intelligence. So it's kind of like it's doomed at the level of what does it mean to discover this very alien extraterrestrial intelligence? Then its technology is something, technology is sort of defined by that connection to human purposes. And it's kind of, in the end, this is basically just saying, go out and observe the physical world and go see how we can pull what we observe in the physical world into into something that is of technological use for us humans. Whether you do that by having a little spacecraft or by using a telescope or by having it be in a lab or by using a computer, that's a secondary issue. I think that this idea. So that's probably that. I don't know whether that's the furthest out, the wildest pitch I've ever heard for a company. Now, interestingly, that pitch was made by a couple of people. One of them is the chairman of an astronomy department at a top university. The other is a CEO of a multi-billion-dollar company. So it's not, the sort of the prior based on, are these people sensible? Yes, they're perfectly sensible people. Is this idea totally wacky? Yes, this idea is totally wacky. I will have to say that I think this idea of going out and sort of exploring the universe with little tiny interstellar spacecraft, one of the things that I find interesting is that this whole idea of Ruliology is exploring the computational universe. And I think that the Rulial space program is, in a sense, more powerful, much cheaper, and more accessible than a sort of physical space program. But it's something that will reveal a lot more. The Ruliad is much bigger than what our spacecraft will sense in the physical universe. And but it turns out the Ruliad, the kind of computational universe, is vastly more accessible to people. And I think it's sort of a great thing to imagine this kind of this citizen science Rulial space program, so to speak, a lot easier than flying actual spacecraft in physical space. But I would say on balance, though, that the technology pitches that I get, while some of them seem much further out, tend to have more meat to them. Particularly when people, well, okay, there are ones where it's just an idea. Those are usually hopeless. But ones where there is, or often hopeless, but ones where there is actually, we built code, we built a machine, there's something there, and that's a good hook to start from. Let's see. Um, okay, Epi asks, is it helpful to explore parts of Ruliology that don't have a chain of experience back to us humans, or is it most helpful to explore the surface area of what has been explored so far related to human-like observers? That's a good question. I mean, I think you can be sort of ambitious and jump to some place in the computational universe that's very unexplored and see what's there and then try and relate it to human experience. It's kind of like look through the telescope, observe that complicated thing in some high energy effect in some galaxy or something, and then try and relate it to what we know. See what's out there and then see how it relates to what we know, versus take the things we know and try and build from that. The same thing occurs in sort of in mathematics. You can go out into the mathematical universe and just find theorems. Those theorems will be most mathematicians will just kind of shrug if you tell them one of those theorems. They'll just say, that doesn't really, I have no context for that. I think there is an opportunity in Ruliology to do the more ambitious thing of just jumping out into the computational universe, finding what's there, and then interpreting it, rather than taking what one already knows how to interpret and sort of pushing one step out from there. I've done both kinds of things. I think that I think there's room for both of them. I mean, there are places where, let's say in Ruliology, one's looking at systems of limited size and one knows they become periodic. And there are all kinds of theories in terms of the group theory of what happens with those things that one can study, and one can look at lots of different cases of that. That's a useful thing to do, and one will extend, sort of generalize that group theory, and et cetera, et cetera, et cetera. It'll be quite interesting. That's something sort of building from what we already know, as opposed to just like, let's look at this kind of system that involves some structure that we haven't seen before and just get a sense of how that works. That second thing I do quite a lot of. I guess that it requires sort of knowing how to do a good Ruliological experiment, a good Ruliological study, keep organized, make things as simple as possible, figure out how to make good pictures, those kinds of things. Those are sort of principles of good Ruliology. Let's see. Double is asking, can AI be used to evaluate all the things that get sent in to me? Probably. It'll just say they're all nonsense. Well, but it might say that it's nonsense when it's something that's kind of unexpected and actually not nonsense. I bet if you fed it the works of Ramanujan, it would be an interesting exercise, actually. Well, it's an impossible exercise now because of the actual history of the world. But had you been back there in 1913 with your LLM and you'd been the G.H. Hardy of the time, and been able to feed Ramanujan's first letter to an LLM and said, does this make sense or not? I think the LLM of the time would have said, nah, it's too far out there. Of course, now the LLM has read Ramanujan's works, so it's kind of, the game's over. But I think if there is something truly creative, original, and important, it's not a good match, probably. I think the LLMs will just pretty much say it's all nonsense because they will have seen these patterns. I mean, I know somebody who's actually contacted me who has a theory of their own, but they've also cataloged 10,000 theories that people have about physics. So there are lots out there, so to speak, and the LLMs will have seen them and will have said, well, this is one that people call a crackpot theory. Now, the truth is scientists have a bad habit of saying that about original things. People thought that the continental drift theory was a crackpot theory. They thought the theory of germs was a crackpot theory. They thought lots of other things in science were crackpot theories that weren't crackpot at all. They were absolutely correct. And so, it is, if you trust the LLMs to just, all you'll have is the past, so to speak, and sort of the sort of development for the future is kind of foreclosed. Let's see. There's a question from RBS about Rule 54, one of my friendly elementary cellular automata, encoding a Collatz problem. How can one use that to search for a proof about the Collatz conjecture? It's the 3n+1 problem. I don't know. I think it's super interesting if there is such a connection. There are certainly things one knows. Well, I think that the real challenge there would be to make such a connection and then to use sort of the other computational characteristics of something like Rule 54 and show that that's connected. I mean, we don't yet know whether Rule 54 is computation universal. If it is, and you can connect Rule 54 to the Collatz problem, then you will effectively proved that there's you will have proved computational irreducibility, and worse than that, you will have proved kind of an embedding of computational universality, within that Collatz problem. It'd be roughly something like saying, if you pick the number you start from, so the problem is you take a number, if it's even, you divide it by 2. If it's odd, you say 3 times the number plus 1. You keep iterating like that. And most of the time, it will sort of decay down to this cycle of, I think, 1, 4 something and 1, 4, 2 or something like that after a while. So far as anybody can tell, it always decays to that cycle. The question is, can you prove that? And if you could show that there exists that you could encode any computation, any Turing machine computation, whatever else, in the initial number that you give, and that running down to the output was somehow encoded any possible computation, then you would have sort of embedded universal computation in this problem. And then a proof about it would kind of necessarily be something where, well, there would be a bunch of undecidability, a bunch of, okay, so here's how it works roughly. So when you have something like that problem, you can say, what's going to happen in the end? Given that I have some initial number, what's going to happen in the end? Can I work that out? How do I work that out? Well, you can just run the steps and see what happens. The question is, can you jump ahead? Is there computational reducibility in the problem that allows you to jump ahead? Or are you stuck just going step by step by step? If you're stuck going step by step by step, then unless you can give an upper bound on how many steps there might have to be that you would look at, then you have to do an arbitrarily large amount of computation to get to the answer. If you want to answer the question, will it ever terminate for all the different possible initial conditions, that's an infinite amount of computational work. That's something you'll just never be able to do in any kind of computational way. But now, if you say, well, like, is it something like, if it has a choice between halting and going into a loop, you can say, well, let me characterize, let me see if I can prove that it will, that such and such a thing is always going to go into a loop and never is going to escape. If the thing halts, it's like it's stopped, it's done, we know what's happened. If it goes into a loop, it could be a very simple loop where it's just repeating the same things over and over again. Then it's easy to sort of prove by mathematical induction that it just has to always be in that loop forever. But if it's doing something more elaborate, it can be more difficult. And the question is sort of the structure of what's happening there. How complicated is that structure? What kind of mathematical things do you need to characterize that structure? So, for example, a very common thing is if you have sort of one generator of what's going on, if there's sort of a mathematical version of a stem cell that's just producing behavior over and over and over again, it keeps on repeating, you can use mathematical induction. So mathematical induction, something known to Euclid, for example, that says we know a thing, we know a result about the case n equals 1, let's say. And we also know that if the result was true for value n, then it would also be true for value n plus 1. And mathematical induction is kind of running along that line, going from 1 to 2 to etc., from n to n plus 1. And just once you know that given n, it's true for n plus 1, and you have the base case, you can just zoom out infinitely on that line, and then you know it's always true. That's essentially an axiom. It's an axiom of Peano arithmetic that says that mathematical induction like that works, that it is the case that if it's true, if you can step through the proof, that it will then, you can conclude that it's always true. But it turns out there's forms of deduction that are more complicated than Peano arithmetic, that are more complicated than just going in a line. In particular, there's this thing called transfinite induction, which is what shows up in set theory, where instead of going through and saying, I've got this thing, n, an integer, let's say 11, then I can prove 12, then 13, et cetera, et cetera, et cetera. It's instead dealing with sets of things. You have to kind of enumerate sets, and that's a more complicated form of infinity that you get to. And so it's a different level of assumption. Transfinite induction is a different level of assumption about when things are true. So it's a different level of axiom system is necessary to make that true. So if you have something where you're trying to prove it, with certain, you have to say, well, with what axiom system? And it could very well be that you just can't get there with any of the existing axiom systems. You kind of have to just say, well, I'm going to introduce new axioms. But by the time you're introducing new axioms, you're not doing something that is sort of grounded to mathematics as we currently know it. When you have these problems that are fundamentally computationally undecidable, that is beyond any of those mathematical axioms. You kind of blew out of the axiom business, and you're dealing with a different kind of things that where there's sort of formal undecidability. Anyway, that was a bit more technical than I was planning to get into here. Let's see. Maybe a couple more things here. Well, question says, as Karl Popper said, falsification is necessary. Self-criticism is important. Does AI need to critique itself? I mean, about AI, it was a common hack from the first days of ChatGPT that it would produce an answer, and then you would ask it next, is what you said previously sensible? And it will say, no, and it will go fix it. That was because LLMs, sort of that generation of LLMs, just sort of write forwards. They're just figuring out what to write next from what they wrote before. So they don't have a plan. They just are going back, and the only way that they can sort of assess what they did is to have it be written down and then go back and look and see what they make of that. More recent kind of reasoning-based models do a little bit more of that looping internally, so to speak. But having said that, it is kind of a myth in the history of science, in the philosophy of science, that this whole falsification thing is a test for sort of the validity of science. That was a thing that, I don't know the exact history of how Popper came to invent that, but it's a thing that only very narrowly works in science. It is, something like natural selection. It's not a falsifiable theory. It's a description of what happens. In mathematics, there are not falsifiable theories. There are in the same sense. I mean, there might be conjectures that you could have that you could disprove and so on, but falsifiability as a kind of a gold standard for what makes sense to explore in science isn't really right. It's made, as a practical matter, it's made very difficult by the fact that experiments are hard, and it isn't the case that like the theory might be wrong, but the experiment, kaboom, once the experiment is done, we know it's telling the truth. Experiments are hard too, and experiments are routinely, absolutely routinely wrong. I mean, particularly in areas like the life sciences, experiments are really hard, really difficult to reproduce, and they're often wrong in the sense that nobody can reproduce them. And I think that, and possibly even known to be done in an incorrect way and so on. So if it really isn't the case that, falsifiability is kind of tends to say sort of experiment is the decider and theory is the one that's challenged. In my experience, it's often the case that the theory can be so clean that you say, I'm really suspicious about that experiment, and you'll be right about that. So it's sort of the wrong way round to think about it that way. I think it's caused quite a lot of trouble in the way that science has been done, the way people think about science. And it's like, is that a falsifiable hypothesis? Well, that doesn't really quite make sense in that sense. It's a more complicated story. Let's see. There's a comment from Elsie about perspectives on impossibility theorems and proofs. Oh, I love impossibility proofs in science and in technology. For example, a lot of the things I've studied about one-dimensional cellular automata, there was a theorem that one-dimensional cellular automata basically couldn't do anything interesting. But the theorem had a bunch of assumptions, which were complete nonsense. But it was a theorem, and given those assumptions, you could prove the theorem. Maybe it wasn't a very exciting theorem because the assumptions kind of had almost cooked the whole thing. But that's the issue. People say, given this, you conclude this. And then they just walk away with a conclusion without knowing, well, what was assumed to get there. And, physics is absolutely full of impossibility theorems. Things about, for example, I don't know, gauge theories, renormalizability of gauge theories, impossible until one realized, oh, well, there's this Higgs mechanism that brings in the unexpected, and so on. And I think I mean, many things I've done had impossibility theorems that said that they couldn't be done. And it's very much like what happens in the computational universe. What's really out there is very surprising, is very much beyond your immediate intuition. You have an intuition. This kind of system is going to work only in this way. And then you see that corner case that you just didn't think of. It just doesn't match the criteria that you used for your sort of the net that you were catching things, or the cage you were putting things in. It managed to escape in some weird and unexpected way. Same thing happens with technology. People say this or that thing just doesn't work, like neural networks. For a long time, it's a classic case of a sort of impossibility-like theorem from neural nets sort of invented in their somewhat modern form in 1943. And then in the 1960s, two people I knew quite well, at least one I knew well, Marvin Minsky and Seymour Papert, who I also knew but not so well, um, wrote this book that basically said, well, what it really said was, in this very specific case, neural nets can't do anything interesting. But what the community took away from that was neural nets are dead. They'll never do anything interesting. And it took, well, about 20 years before people started looking again, and another, well, 30 years after that before people really, before a bunch of discoveries were made about deep learning and so on. But that was a case where, yes, there was sort of an impossibility theorem, and everybody went and concluded that it was hopeless and you shouldn't even look at those kinds of things. I think, actually impossibility theorems might be good if you're looking to make a great advance in science. Poking around the impossibility theorems might not be a bad thing to do because they're usually, it's like they're usually not right. I mean, it's kind of reminiscent of the statement made around 1900 by some patent examiner, I think, that all inventions that are worth making have now been made type thing. It's like the things you don't think of. It's like another thing I hear people, friends of mine, who say sort of technology development has slowed down. There's nothing interesting. It's all just, social media companies or whatever else. That was at one time at least. But then what you realize is what that means is in a well-developed category that you can talk about, that category is well developed, and so it's advancing slowly. But that doesn't mean there isn't some interstitial category, some new area that's just exploding, but it wasn't one of the things you were thinking about. It wasn't the thing that you already knew about. It wasn't the thing about which you could have some kind of incremental progress. So I think that the that's that's a sort of a mistake of how to think about things. The things that we understand and they're not going to develop as much. The things we don't understand, the places where lots of development happens. Now, it has to be said in technology, there are plenty of, oh, so and so tried it and it didn't work, and so it's impossible. That was a particular affliction in computer science, particularly before the modern sort of explosion of people doing computer science at an academic level and so on. It was a very, very, very common thing that you would hear. Oh, so and so tried that and it didn't work, and therefore that is a dead story. When we built Wolfram Alpha, for example, there had been decades of failures in making general question answering systems, and to the point that people said, "Oh, that was a thing," and it just didn't work, so to speak. Actually, a story I've told many times, Marvin Minsky, who I happened to mention earlier, I saw him just before Wolfram Alpha was released and was sort of demoing it to him. And he was like, oh, not paying really any attention because he'd like seen 100 other question answering systems that hadn't worked. And when I finally said, Marvin, you should pay attention, it actually works. And after a little while, he was like, oh my God, it actually works. Good for him for being able to pick that up quite quickly. But it was very much a kind of thing where people said, "Oh, that kind of thing just doesn't work." People tried it and it didn't work. So the same thing happens in science. People tried it and it didn't work. I mean, there are also cases where people build up these giant mythologies about how things should work, and they and people do huge amounts of work on it, and it just there was nothing there. It was just pure kind of mythology about what might be, and sometimes driven by sometimes almost political, sometimes kind of technological kinds of. But if it was true, it would be so wonderful type things. Um, okay, my last question for the day. Eli is asking, um, uh, Out of curiosity, do you enjoy getting these emails? No, I don't. They make me sad because I feel, I'm really a person who is very big on taking whatever each of us humans sort of can do and making it flourish as much as is possible. And taking people's skills and energy and talents and so on and directing them to things where they can be as productive as possible. And when I see these things that people sometimes have obviously spent a decent amount of time on, and it's like, but that time just didn't add up to anything. It wasn't going in the right direction. If that person had been studying some Ruliological thing, then they would have made something which in 50 years somebody will pick up and say, hey, that was interesting. And whereas the things that I'm seeing most of the time are less like this is terrible. In fact, I feel better about things where somebody will say, "I had this great idea yesterday, and I'm now writing you this 2 paragraph email about it." That's like you didn't waste any time, you know, nothing was lost here. It was just all a bit silly, as opposed to something like the chap that I was talking about from 1975, where it was just like a lot of work had been put in, a lot of work. And it's just like this was a misfire. This was, given that you were going to put that work in, if you were studying little hoops of wire that do this or that, well, if you'd studied, linear motors or something, or ways to configure, electrodes to produce some interesting electrical effect, that would have given you mileage. That would have been a thing that was important. That would have been a thing that had consequences, as opposed to a thing where you just have to say, sorry, that was the wrong idea. So I'm always disappointed when I see kind of work, lots of work that sort of is kind of getting thrown in the trash. I mean, this happens to me, since I run a tech company for a living. It's one of those things that occasionally happens is there'll be some project and it's been done, and lots of energy has been put in. It just was a really bad idea. I mean, it's my responsibility as CEO to prevent those kinds of things happening. I think I do a rather good job generally of that. Um, but it's something where it's kind of, to me, it's a sort of a tragedy if all that work was put in and in the end it got thrown in the trash. And that's kind of my feeling is sort of a feeling of tragedy in getting something where there's a lot of work and it just doesn't, it was a misfire. It wasn't really in the right direction. And that's why I think if one is seeing, for example, Ruliology, where it was done well for what it was. It maybe is a disembodied thing that doesn't yet have a place to fit in, where it is that last puzzle piece that does something amazing, but it's a solid puzzle piece that one can kind of keep, like sort of puzzles from antiquity or something. Those puzzles are probably a bit difficult to fit together these days, but you can imagine that those puzzle pieces are still there, and now you can fit the puzzle together, so to speak. So I think that's what would sort of makes one feel good about what people do. Is this is a thing that is sort of a surviving contribution as opposed to something where lots of effort was put in and it's sort of all wasted. So, okay, well, we should wrap up there, but thanks for joining me for what was supposed to be mostly just a reading of a piece that I'd written, but I guess we spent longer on the Q&A than on the piece I wrote. But that's probably all for the good. Well, my parting comment is learn Ruliology. It's really fun. It's really valuable. It really can be done, and I'm looking forward to being able to provide more resources to do that. Thanks for joining me, and bye for now.